begin. So anyway, it's very nice that Phil Sosoe from Cornell is here, and so he'll be talking about the collapse of the 5-3-2 ensemble. So please start, Phil.
All right. Thanks everybody for coming. It's very nice to be giving a talk. This is joint work with Q and Seong, who is a postdoc at Cornell at the moment. And I'm going to be giving a talk that's hopefully accessible really to probabilists, not go too technical. But of course, if you have questions and you want to see more or hear more about the specific results, I'm happy to send a preprint that will be online soon anyway, and also to explain more. So we'll start with some background from way back. There's a paper in JSP by Leibowitz, Rose, and Spear. It's a very well-cited paper. It has almost 400 citations because it started a whole field. So let's look at what these guys were doing. They were considering objects that are pretty classical in probability, which are Gibbs-type measures based on Brownian motion. But why were they considering them? They were interested in measures that are formally invariant for some deterministic dynamics. The deterministic dynamics that they were studying was the nonlinear Schrodinger equation. This is not a PDE talk, so it's not so important exactly, what the Schrodinger equation is, except in its relation to the measures that we'll be studying. But this is the linear Schrodinger equation on the torus. So here we'll take periodic boundary conditions, and it's an equation for a function u that has two components, real and imaginary. So u is a two-component vector, and the equation is that I dtu is the second derivative in time of u plus some nonlinearity. And then we also have a linear term that will be useful, but not super crucial. So what are the measures that these guys, so you may recognize some names here, these statistical mechanics guys, why were they interested in the Schrodinger equation, the nonlinear Schrodinger equation? Because the nonlinear Schrodinger equation doesn't really have too much physical relevance. There's some, it appears as an approximation for some other dispersive equations, but it's not a really fundamental equation compared to the linear one. So their motivation was to study measures that have this formal expression. So they're measures on functions on 0 to pi, so periodic functions. And we sample the function according to the density minus 1/2 the gradient of u squared. So in this case, it's just one-dimensional. We just have the derivative of u here squared. And then either plus or minus u to the p. The p is going to be the same as the p over there. P does not necessarily need to be an integer, but it can be. And then we also have the minus u squared. And this is with respect to the formal Lebesgue measure. And as we know very well from probability, the proper way to interpret this type of measure is in terms of Brownian motion. You can think of this part here, the quadratic part with the gradient. You can think of this as being a density for Brownian motion. There's many reasons why. One of them is if you take a linear line approximation of u, then you get formally the heat kernel. Or if you expand u into its Taylor series formally, then here you'd get that the Fourier coefficients of u are independent and have variance n squared. And that type of series, meaning the series I'm talking about, is something like this, e to the I n x divided by n, and then maybe gn here, are IID complex Gaussians. This is almost Brownian motion. It's actually a Brownian bridge with its spatial mean subtracted. So for most purposes, it behaves like Brownian motion. So Leibowitz, Rose, Spear, of course, were well aware of this. So they said, we want to study this measure, this classical object here. But our base measure is going to be a two-dimensional Brownian motion. It's two-dimensional in the sense that it has two components. So it's the time parameter is one, is on 0 to pi, but it has two components because u, the solution of NLS, will have two components. And then what we want is we are going to average over all possible starting points for the Brownian bridge. And then we'll have our weight here that has the nonlinearity and this linear weight that if we would, we could incorporate into the measure. Okay, so why are they interested in this? The reason they're interested in this is because this measure, they expected, for reasons that I'll explain immediately, that it would be invariant for NLS. So NLS is a deterministic dynamics. So it means you can, for some initial data, for example, if the initial data is fairly smooth, so if it's say for example, it has one derivative even in dimension one, then you can easily solve this equation using a contraction principle and the Sobolev inequality. So for some initial data, you can find a solution. Maybe the solution exists for a long time. If you're able to show that it exists forever, then one thing you could ask is, what if I take the initial data to be random? What happens to the solution after a long time? And what Leibowitz, Rose, and Spears said is, well, based on an analogy with finite dimensional Hamiltonian systems, this procedure, if we sample with respect to that measure we just discussed above, not quite, because there's going to be a problem if we put the plus sign, but if we sample with respect to that measure, then an analogy that I'll explain in a moment suggests that actually at later times, the solution sampled from this Brownian motion with that weight will also be a Brownian motion with that weight. This is a very strong statement in terms of just PDE, because, for example, it would mean that if you start with u0 of x, that is sample with respect to this measure mu, and then if you knew that we're invariant, then at later times you would have the same distribution. So, for example, the modulus of continuity of u would be preserved. It would be almost surely the modulus of continuity of a Brownian motion. This is something that is impossible to show deterministically. It's not just impossible because it's very difficult, it's just impossible. This equation is not well posed in C alpha spaces. You always lose derivatives. Okay, so this is a very unusual, it means they're very unusual solution, even though they're generic in some sense because they're sampled at random. So why did they expect that it would be invariant? Why did they expect that if we sample from this measure up here and we run the nonlinear Schrodinger equation, we get again something that is distributed at all later times as this distorted Brownian motion? The reason, as I said, is because you can think of the nonlinear Schrodinger equation as a Hamiltonian equation. You can think of it as being generated by starting from this function here. So this function here is very closely related to the function we had in the measure. Basically, the measure we were looking at is a Gibbs measure with this Gibbs weight. And unless formally, you can write it as dtu is equal to minus I times d by du bar. What d by du bar means is that you would take the functional derivative formally of h with respect to u, right? You'd replace here u, the function u, by u plus delta times a small perturbation, and then look at what you get, and then you get some functional of u, and this functional you put on the right-hand side of NLS. Now, why did that lead them to think that the measures would be invariant? This is just based on an analogy with finite dimensional Hamiltonian dynamics. It's not really important what Hamiltonian means here. It just means an ODE of the form that's displayed here. So you start with a function h, a function of two variables, say p and q, or two n variables if the dimension is higher, but let's say it's just two variables. And then you take the gradient of this function. So you put it here, dp dq, but you rotate it by this matrix minus 1, 1. Okay, so this you put on the right-hand side of just an autonomous ODE. So d by dt of p, the vector p and q, is equal to this rotated gradient of h. This is what it means to be a Hamiltonian system for us. Now, there's an analogy between this and NLS. You can look at the real and imaginary parts as two components of this function. Of course, now it's an infinite dimensional system. You can think of the minus I as being akin to this rotation. And on the right-hand side, we have something like the gradient of a functional h, a function of the real and imaginary part. Now, two things just at the level of basic finite dimensional ODEs that are special about Hamiltonian dynamics is that we're looking, when we're solving this equation, we're looking at an equation d by dt is equal to a vector field applied to PQ. And this vector field is divergence free. This is just because of the structure of H. And if a vector field is divergence free, if you look at the flow that it generates, it's incompressible, right? The determinant of the Jacobian is equal to 1. And this is just because this divergence is what you get when you look at the infinitesimal, the derivative of this determinant. Okay, so what that means concretely is that it means that if I start with some initial data, PQ, and I solve this ODE and look at PT and QT, so this is a function of the initial data, and I integrate some nice function, dpdq, then this is the same as integrating with respect to the initial data. The flow disappears. Now, this fact here, the fact that that x is divergence free, also means that if I look at d by dt of h, of p of t and q of t, this is also 0. So this function h is also preserved along the flow of this ODE. So we can print it here for free as part of the measure. This means if we construct a Gibbs measure that's of the form e to the minus h dpdq for this finite dimensional ODE, as long as h is reasonable enough so that we can solve the equation, we expect it to be invariant. Does that make sense? Okay, so they said, well, this is true in finite dimensions, so it ought to be true in infinite dimensions, since we can so nicely represent the Schrödinger equation in this way. Okay, so that was their goal. Well, to do this first, you should talk about whether the measure makes sense. And again, this is a fairly classical problem. One case, which I haven't emphasized this too much, but there's two possible signs in the nonlinear Schrödinger equation. Let me just go back so you see this. There's two possible signs here. Over here, and these corresponds to two possible signs in the Hamiltonian. For short time, this basically doesn't matter. If you're just interested in knowing that there are solutions for short time, the focusing and defocusing case, that's how they're called, the plus and minus signs, don't really make a difference. But for the long time behavior, the case when you have a minus in the Hamiltonian, say, the focusing case, is very different, because then the Hamiltonian is not sign definite. Okay, the Hamiltonian is a conserved quantity, but if this conserved quantity is not sign definite, then there could be energy that moves between the gradient part here and the nonlinear part. And this is a whole, there's a whole theory behind this that's very complicated. But for us, this has consequences. It has immediate consequences that are very easy to understand at the probabilistic level, because the result of putting a plus or a minus sign is quite dramatic. If we just think about the minus sign, then there's really nothing to say. If you put a minus sign there, you're trying to integrate e to the minus 1 over p u to integral of u to the p, where u is a Brownian motion, or basically a Brownian bridge. So it's continuous almost surely. So this integral makes sense, and you're just looking at e to the minus something positive, so that's less than 1. So there's no issue in defining this, right? This is just what it is. It's you take a Brownian motion, or you take a Brownian bridge, you plug it into e to the minus, maybe you add the integral of u squared, and you take the expectation. It's something, maybe you can try to compute it, but in any case, there's no issue of whether this makes sense or not. The situation is quite different if we look at the focusing case, if we try to put a plus sign in front of this integral. If you try to put a plus sign in front of the integral, I haven't really emphasized this, but then the measure doesn't make any sense, right? And the reason is just because if p is bigger than 2, which is the case that we'll be interested in, then you're trying to do something like integrating e to the x to the p multiplied by a standard Gaussian. And since p is bigger than 2, at infinity, this doesn't integrate. And the integral version of this is just that this nonlinear term is much bigger than the quadratic term. So even though the Gaussian has this gradient term in it, it's not enough to control this nonlinear term. Okay. But the reason why Leibowitz, Rose, and Speer really wanted to look at this case, I mean, you could say, well, it would be interesting to note that you can have invariant measures even in the defocusing case, and indeed, that's you could say that that's the case. But they were particularly interested. They thought the focusing case was particularly interesting because in the focusing case, there's the hope that the invariant measure could replace a conservation law that you don't have. right? You have a conservation of the Hamiltonian, but this conservation of the Hamiltonian only holds when you have sufficient regularity, right? You need to know that the Hamiltonian makes sense. But if you think about the Brownian motion, the gradient, the integral of the gradient square doesn't make sense. So if we were able to show that this measure in some sense exists, then it being invariant could be a replacement for a conservation law at a lower level of regularity. So it would be really great if we could make sense of this measure. Okay, so what they did is something very classical for physics. They just added a mass cutoff. But there's an important point here is that this mass cutoff is appropriate for the equation. I'll mention this in a second. Okay, so what they did is they just said, instead of looking at just the expectation of e to the 1 over p and then the pth power, the integral of the pth power of u, and then this quadratic term, they also added the restriction that the L2 norm is bounded by k. The reason why this is appropriate, and why I mentioned it's appropriate for NLS, is that NLS, as an equation, formally at least, satisfies conservation of mass. So if you have a solution of the nonlinear Schrodinger equation, and you look at it at some positive time, its L2 norm is equal to the L2 norm at later times. So that putting some restriction, any sort of function of the L2 norm inside of this expectation is not going to, spoil your chances of being invariant. Okay, so it's not just, of course, you could say, well, I could put anything here, right? I could just put like e to the minus something like u to the 1000 or something like that. But that would not be very useful, right? Because you don't have any information about invariance. You'd completely destroy the hope of being invariant. Whereas in this case, adding this cutoff still maintains that hope. So what did Leibowitz, Rosen, Spear show in their paper? They showed that as long as p, the power here, is less than 6, and you choose any cutoff k, then the partition function is finite. If p is bigger than 6, then they show that the partition function is infinite for any choice of k, positive. And then I'll talk about the case p equal to 6. But first, let's discuss how could we have guessed that p is equal to 6 is important. There's two ways to guess it. One is more analytic and the other is more probabilistic. So formally, maybe let's start with the more analytic way. Formally, the measure that we're interested in is the Brownian motion. So Brownian motion is this quadratic part here. And we're integrating the nonlinear part with the restriction that the L2 norm is less than k. So now let me remind you of some inequality that you may have seen, or you've certainly seen in some form or other, a Sobolev inequality. In this case, this is the Gallardo-Nirenberg inequality. It's an interpolation form of the Sobolev inequality that is very important. And what it says is that if we want to control the pth power of u in dimension 1, we can do this in terms of the integral of the pth power of u. We can do this in terms of the gradient of u in L2 and u in L2. Now, this is great because these are exactly the quantities that appear, at least formally, in this partition function, right? So if we assume that u is bounded by k in L2, so if we add this to our partition function, then we can control the nonlinear term in terms of a power of the integral of the gradient square. And this power is p minus 2 over 4. So if p is less than 6, this is a power that is less than 1. So it suggests that this Gaussian term is going to dominate, and that in fact the partition function will be bounded by the partition function of some Gaussian, possibly with a slightly smaller variance. Okay, so it should be finite. And this argument, although it's a bit difficult to make sense of it directly, it can be more or less implemented, and it can also even give you, suggest what should happen when p is equal to 6. When p is equal to 6, the question of whether this term, the nonlinear term, or this term dominates is going to be more delicate, and it's going to depend on this the constant c of k, the constant that appears in the Gallardo-Nirenberg inequality. Indeed, Bourgain, for p is equal to 6, using some some arguments, but using some Littlewood-Paley argument is basically using a Sobolev inequality. He showed that if k is very small, so if you restrict your Brownian motion to a total integral, the integral of u squared, to be very small, then even in the case p is equal to 6, you can integrate this partition function. We later showed with Leonardo Tolomeo and Tadahiro O that if p is equal to 6, then you can actually construct this partition function all the way up to k equal to the mass, so the L2 norm of the minimizer, the optimizer in the Gallardo-Nirenberg inequality. And the optimizer here actually gives you the best constant. So in that case, you'd think that this term, so the nonlinear term, and this term are exactly matched. They're basically integrating something like e to the 0. And the surprising thing is that even when k is equal to this, so when you're integrating e to the 0 over this infinite dimensional space, you still get something finite. And the reason for this is that you're not really integrating e to the 0 because for most functions, the Gallardo-Nirenberg inequality is not sharp. You have to be very close to being a soliton. So you have to be close to a basically finite dimensional manifold. And by choosing coordinates correctly and doing some spectral analysis, you can show that this partition function actually is finite, including at this exact threshold. Okay. So this is the analytic reason for this p is equal to 6 threshold. Another way that you can think of it, of the p is equal to 6 threshold, is more probabilistic. You could try to just compute this expectation, e to the integral of u, so I removed the constant, e to the integral of u to the p, with the restriction that u in L2 is bounded by k. Of course, what you can do is, since you knew that u in L2 is bounded by k, you can take out the maximum of u to the power p minus 2, and then multiply this by k, and then you see that you're just trying to integrate, or you're just trying to compute or find the tail of the maximum, or you'll be able to compute this if you know what the tail of the maximum of the Brownian motion is, conditioned or not conditioned on the event that the L2 norm over the entire interval is, say we're trying to compute this, conditioned on the L2 norm is less than k. Okay, so this seems like a very classical type of computation. I don't think I've seen this in a book, but it seems like exactly the sort of thing that you would want to study when you look at Brownian motion, except that usually when we study Brownian motion or Brownian bridge, we don't really care about its, the integral of it over the entire interval squared. But still, we can heuristically compute this, and then this can be made rigorous. Of course, we can ask, well, suppose I put this condition that the total integral is less than k, what needs to happen if I want to have a maximum of size m? Well, if the maximum is of size m, then it can only occur in an interval of size 1 over m squared, right? Because if I look at the total integral of u, this has to be bounded, and so this puts a bound on m, that would be the maximum, squared times the interval where the maximum is occurring, right? So basically, near the maximum, if the maximum is m, then you can only take this maximal value around in an interval of size 1 over m squared. Of course, this is fully heuristic. So this means that near the maximum, your Brownian motion conditioned on the L2 norm being less than k looks like this picture over here. It looks like a function that has a peak of size m and has a base of size 1 over m squared, right? So let's call this function psi m. The probability that we see Brownian motion behave like this is roughly, by the usual arguments, is roughly like e to the minus the gradient of psi m squared. But if you compute this gradient just by scaling, you get e to the minus m4, right? And this m4, it has to beat this guy, mp minus 2. And so you see that p has to be less than 6 for this to have a chance to work. Does that make sense, roughly? Okay, so this is the probabilistic heuristic for p is equal to 6. Okay, so this is just the construction of the measure. This is what was achieved by Leibowitz, Rose, and Speer in 1987 in their paper, and that's where they left it. they said, okay, well, we can construct a measure, but we're not able to construct invariant dynamics. And basically, the only thing that, well, not the only thing, one of the things that was missing for them to construct invariant dynamics, and that was extremely difficult, despite their great powers, is they did not know how to show that you have solutions of the nonlinear Schrodinger equation with initial data that looks like a Brownian motion. The Brownian motion has basically 1/2 derivative, and at this point in the 1980s, when they were studying this problem, it was not known how to construct solutions when you don't have at least the integral of the gradient squared finite. This was a very difficult problem in Fourier series or harmonic analysis, if you wish. And who better than Jean Bourgain to solve this? In the 1990s, he got very interested in this problem, and actually some of his most famous papers, his most famous PDE papers, were based on this problem of finding low regularity solutions of dispersive PDE. And one of the motivations that he gives is using Brownian motion as an initial data. So he was able to, he made dramatic advances, actually ahead of getting his Fields Medal, where he was able to show that you get solutions. So deterministically, if you have initial data that is basically as bad as being in L2, so certainly good enough, Brownian motion is certainly good enough, you can find solutions locally in time. And then the beautiful fact is that he realized this promise that I discussed earlier, is he showed that in the focusing case, you can use the invariant measure to construct global solutions. And he invented actually for this a very, very interesting argument, because to discuss invariance, usually you have to have global solutions, and you don't know that you have global solutions because of this possibility of blowup. It's actually known that you can have blowup solutions in the focusing case. And so he used the invariant measure as a replacement for a conservation law, and he proved the global existence at the same time as the invariance. And so that was a great achievement, but this is not really something. So this is not really what we want to focus on today. What we're interested in is, Bourgain also got interested in this later, is what happens when we take the infinite volume limit. So what happens to these measures when we take not a fixed circle, 0 to 2 pi, but we take a large circle of length 2L. So we're looking at the same object. Let's look first at the defocusing case. We start a Brownian bridge. I don't know if I explained this. This is a Brownian bridge. Started at A. Remember, this is a two-dimensional Brownian bridge. We integrate e to the minus the LP norm, but to the p. But now it's on a longer interval, on an interval of size 2L. And we also have our quadratic term. And then we have a partition function here. And we want to know what happens to this measure. What do the paths look like when L is very large? Okay. So in the defocusing case, in the case where this sign is minus, this is a very classical computation from probability or mathematical physics that you've probably all seen in some form or other. Let me remind you of this. This is sometimes called a ground state substitution. We can apply it in general when we're trying to estimate, or this is very classical in large deviation theory, for example, when we're trying to estimate something like the expectation of the integral of minus L to L of V of U, where V is some potential, maybe some reasonably nice function that is, but it needs to be bounded below. Okay, so if it is bounded below, like in this defocusing case, we can do a nice little transformation, nice little computation using Ito's formula by involving the ground state, so the first eigenvalue of the Schrodinger operator with potential V. And this is sometimes called a ground state substitution in math physics or in physics. And if you do this Ito computation, then you see that this term here, you can interpret it as an Ito term coming from applying the Ito formula to the log of phi. Okay, so in this case, we're looking at periodic boundary conditions. So this log of phi L minus log of phi minus L is just going to cancel. And we're just left with this thing here, the logarithmic derivative of phi minus the integral of its square. And this, of course, we recognize. So this is du, this is stochastic integral. Of course, in the periodic case, we have to be a bit careful what we mean by the stochastic integral, but let's not worry about this. If it were just a Brownian motion, then this factor here would be exactly the factor that we have for Girsonov. And this would change our original, Gibbs measure. It would reveal that, in fact, this Gibbs measure was nothing but a diffusion bridge with generator given by Brownian motion plus this drift dx log phi. And once we have this, it's very easy to take the limit when L is very large, because then you're looking at a diffusion. So provided the potential grows enough at infinity, it will have an invariant distribution. So when we take the limit, we just find a stationary diffusion on R, right? We take the limit as L goes to infinity. This thing, which originally was presented as a Gibbs measure, is revealed to just be something very boring, just a stationary diffusion on R, with this generator where phi is the ground state of this operator here. Everything okay? All right, so this is some classical stuff. Unfortunately, as I said, for this to work, for this type of like Feynman-Katz or whatever you call this type of stuff to work, you need to have a bound below on V. Otherwise, things don't really work. So
V was mod x to the power p here. Is that
yeah, so it's x to the power p or x to the power p plus this quadratic thing part here, right? So this guy we can write as e to the minus the integral from minus L to L of V applied to U dx, right? And then we can perform this this calculation. Again, you have to be a bit careful, because here I want to look at the Brownian bridge. For Brownian bridge, you have to you have to adapt this calculation as in the usual ways, so that to apply Girsonov, because it's not it's a bit, it has this if you want to view it as a semi-martingale, it has this nasty drift when you get close to the end. But this is just some technical stuff. In spirit, there's no big difficulty here. So there's no mystery, and unfortunately the situation is a bit boring. Okay, so this is if we have the minus sign over here. If we have the minus sign over here, let me say it again. If you have the minus sign over here, in fact, I could have mentioned this at the very beginning. This is it's sort of deceptive to write it as a Gibbs measure. In fact, it's just a diffusion. It's just some version, maybe a periodic version of a stationary diffusion. And this is a very well-known object that we all know and love or don't love, depending on your inclination. Okay.
Yeah, thanks.
Everything okay? All right, so let's look at what happens if we take the plus sign. If we take the plus sign, the situation is quite a bit more difficult. And actually, for a while, there was some confusion about this. If we take the plus sign, first of all, remember, we have to add in a cutoff, right? We have to specify that the L2 norm is bounded by some number. But here, since we want to take L to be very large, we cannot just take a fixed number, because you'd be saying that the integral of U in L2 is fixed, whereas you take a larger and larger interval. If you ask that it be fixed, bounded by a fixed number, the fact that we integrate here over all starting points makes this measure actually rotationally invariant. It makes it stationary. So it would mean that you're asking a stationary field to have integral bounded by a constant. So you cannot get anything. You cannot get anything serious. So we need to allow the whatever particle number, whatever the mass, to grow with L. And the correct way, I think, or the way that we would expect it, is that it grows linearly. Okay, so this limit was considered by McKean, who also, I should have mentioned, in the 1990s, McKean also worked on the problem of constructing invariant dynamics. It was considered by McKean, and McKean has a couple of papers that are, they sound very impressive, and he has many great ideas in them, but ultimately they're wrong, because he actually thought that you get something, you get some sort of limit that is quite mysterious when you take L to infinity. But as we'll see, the limit is not mysterious at all, and it was found by McKean's student, Brian Ryder. So Ryder, in a very nice paper, it's very short, it's about 20 pages in CPAM, he resolved this problem and also resolved some of the confusion that was introduced by McKean himself, unfortunately. because I think he is too smart sometimes for his own good, and he had so many ideas, but none of them were fully, he just said, well, I take the limit and I get something, it would be nice to know what. And Ryder did this a bit more carefully. He said, okay, well, let me first start with the partition function. What happens when I look at the partition function? This should be a classical problem from large deviations or whatever. And indeed, he computed the partition function. So the partition function is, remember, you integrate over all starting points. So here's a starting point. The starting point is in R2 because it's a two-dimensional Brownian bridge. Then you run a Brownian bridge from A back to A, and you integrate e to the 1/4 minus L to L u to the 4 dx. I changed p to 4 because that's how it's written in Ryder's paper. There is no doubt that Ryder could have done any p less than 6. You just get a total, I mean, it's a completely trivial modification. And then we put here this condition. Oh, sorry, things moved. You put here this condition that k is less than L. He computed the partition function. He showed that when you take the limit as L goes to infinity, 1 over L cubed log of ZL, you get, as is tradition for large deviation type result, you get a you get a variational problem. And this variational problem, no surprise, is closely related to the formal expression we had for the Gibbs measure. I'll remind you of this in a second. And this could give you some hope. It says the first order behavior of this process is given by this variational problem. Maybe there's some interesting lower order behavior that we see. But unfortunately, as we'll see, once you understand this even at a sort of formal level, you quickly realize that any limit of this has to collapse to the 0 path. So this limit of this measure, when you take L to infinity, is just a measure of the delta function on the path that's identically equal to 0 on the real line. Is the statement clear? Okay, just a second. All right. Let's continue. So let's just look heuristically at why Ryder's theorem makes sense. And the reason I want to go through his theorem is that once you understand his theorem, what we did with Kuhn also will not require much explanation. Actually, I'm not going to explain. I'm just going to tell you what our result is. So let's try to understand what he did. Very classical math physics stuff with just a little some extra twist, but it is a very nice computation. You should really look at this paper if you like Brownian motion. So he said, this is the partition function. Let's think of it as this is not what he said. This is my interpretation. So anything that doesn't make sense should be ascribed to me. Write this Brownian motion as this free field with the gradient of u squared between minus L and L du, where du means with respect to all the functions, all periodic functions on minus LL. Now let's do a change of variables. Let's, whatever that means exactly, in this du, let's replace u by L times V of L. So here V is some fixed function, but we rescale it by L. The reason we want to do this is that if we rescale u like this, then we see that these two terms, the u to the 4 term and this gradient u squared term, obey the same scaling in the following sense. Once I do this change of variable, meaning once I plug in u is equal to L VL, and I change variables setting Lx equal to y, then I increase the size of the interval from L to minus L squared. But I get rid, or I see that there's homogeneity in this L cubed parameter. And then this problem is revealed as a very classical large deviation problem, right? So it seemed at first to be maybe some mystery, but then it's just some large deviation problem. It's almost disappointing. When L goes to infinity, we can extend this L squared to infinity. So whether we can is a good question, but let's say we can. We can extend this L squared to infinity, and then remembering that we've replaced u by LVL and that we had the condition that u is less than k times L. Undoing that conditioning, we just find that v has to be less than k. So basically, we're interested in finding the large L limit of something like an integral du, but now it's over all function, or I should write here dv instead of du. And now v is functions that are, you know, since we're doing things very heuristically anyway, you can just think that we're now looking at functions on R. And we restrict their L2 norm to be less than k. And we're integrating e to the minus L cubed times some nonlinear functional of v. Okay. So, of course, by the Laplace principle or whatever, we expect that this is going to be very strongly concentrated around the minimizers of this functional VH here. But the minimizers of this functional, that's exactly where we get this this HR of V here. So it's the functional is the gradient squared minus the integral of V to the fourth. And we have the condition that the L2 norm is equal to K. But by rescaling the function, we can see that this is just K squared, K cubed times the infimum of another functional, but where now we minimize over functions whose L2 norm is fixed, is equal to 1. Now, and this is highly non-trivial, but it was figured out in the 80s, and maybe 70s and 80s, and now with modern technology, it's much easier to prove that the minimizers here, sorry, here there's some typos that I'm going to, not that it's super important, but let me just, so in this case, it would be 2. Yeah, so I guess in this case, it's okay. In this case, it was fine. I can leave it like this. Everything is 2. Sorry, my eraser doesn't work. Okay, so the minimizers of this functional are actually many, because it's a functional that is, it has scaling invariance, for example. You can rescale. But if you ask that they be radial, it's translation invariant, not rescaling, it's not scaling invariant. It's translation invariant, and you can multiply by a constant that has modulus 1. So if you ask for the minimizer of this, you cannot get one single function, but you can classify them. If you ask that it be positive and radial, then the minimum, so you remove this translation invariance, then the minimizer actually has this form. It's the solution of this elliptic equation. This elliptic equation was also very well studied in the 80s and early 90s, this type of nonlinear ground state equation. It's known to be unique up to translation and modulations as a minimizer of this. And this equation here is just the Euler-Lagrange equation for this variational problem. So what that means for us, if we assume that when your energy, when H is almost 0, then you have to be almost a minimizer. This is not a given, right? This is something that is highly non-trivial, even for classical inequalities like the Sobolev inequality. This is actually fairly recent stuff. There's a lot of stuff. There's a lot of work on stability for functional inequalities, saying that if you're almost a minimizer of some functional inequality or variational problem, then actually you must be very close to the minimizer. The reason why this is sometimes difficult is that in finite dimensions, you would just compute the second variation and then look, maybe you have some quadratic error. But in a lot of these problems, there's more than one minimizer. So there's a lot of degeneracy, and you may not actually be able, like the second variation may have eigenvalues. So it's a lot of work, and it has to be done on a case-by-case basis. And even for inequalities that are fairly reasonable, it's not so easy to see. But thankfully for this inequality, which is closely related to the Gallardo-Nuremberg Sobolev inequality, it was done in the mid-90s, and then there's been some revisiting of this by people like Rupert Frank in the last 10 years. Okay, so if we accept that if you're almost a minimizer, so in this if you're trying to evaluate this integral using the Laplace transform, Laplace principle, then you would see that the partition function, the main contribution would come from V, for which H of V is almost equal to 0. Well, we know that the minimizers, the ones for which it's not 0, it's equal to its minimum. We know that the actual minimizer is this function, a given function, and its translations and modulations. Then, if we knew that, as long you have some sort of coercivity, as long as you get away from this, from as soon as you get away from this type of function, then you actually will be, h will be much bigger. Then that suggests that the main contribution, or that the typical path that you see when you look at this ensemble for large L, is very close to LQL. Okay, where does this L come from? Remember, to get to the variational problem, we actually did a change of variables. So if V is close to Q, well, V was related to U by a change of variables in L. So basically, what Ryder was saying, although he did, I presented it in this way, but if you look at Ryder's paper, it's all computations just using Brownian motions. He uses no fancy stability results for Sobolev inequalities. Everything is just done by hand. It's very beautiful. But basically what he's showing is this. He's showing that the typical path when L is large has to be very close to a rescaling of Q, this ground state. The ground state of this elliptic equation, if you think of it as a perturbation of the case where you don't have this Q cubed, then this would be something that decays extremely quickly at infinity, right? It would be some solution of a massive Laplacian with a mass term. So it is also the case that Q with the nonlinearity, so the solution with the nonlinearity, also decays very quickly at infinity. So basically, you're saying that if you look at the typical path, it looks like a Brownian motion deformed to be close to this LQL. Okay, but LQL is a rescaling where you make space, you make space much smaller and make space pass you much faster. So it looks like this ground state that is centered around some Q, some point x0, and its width is 1 over L, and its height is L. And away from this ground state, you decay exponentially. Now, of course, you don't really have exponential decay because there's still fluctuations. These fluctuations, what Brian Ryder doesn't quite show but suggests, is that they're order L to the minus 1/3. The reason for this L to the minus 1/2, the reason for this L to the minus 1/2 is that it's the L coming from the rescaling times L to the minus 3/2. The L to the minus 3/2 comes from this L cubed term here. If you believe that after removing maybe some bad directions, there's going to be a few bad directions. For example, you can rotate the soliton, or you can modulate the soliton. So there is a finite dimensional manifold of minimizers here. But if you're away from this finite dimensional manifold, you can actually show that this H has a quadratic behavior. So that suggests that the fluctuation around this soliton manifold are of order L to the minus 3/2. When you multiply by L, you get L to the minus 1/2. So all of this in 20 pages with no modern technology, not every single statement that I gave, but this is basically what Brian Ryder realized. This is what he showed. And this is it's an extremely nice result. So I strongly invite you to take a look at it. Does this make sense? Okay, so finally, remember I said that this means that basically you don't see anything interesting. The reason it means you don't see anything interesting is that because we've integrated it over all starting points, the measure is completely translation invariant. So it is rotation invariant. So you can rotate the coordinate on the circle so that this x0, the point where the soliton is centered, the point where LQL is centered, that point is going to be uniformly distributed on the circle. So basically, you're looking at a very, 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 very large circle somewhere. So this circle has size L squared. Somewhere at a uniformly distributed point, there's a width 1 over L interval where you see a peak of height L. Of course, this measure, if you look at any reasonable topology, like if you're asking what's happening here, you will never see this peak. Even though it's very high, you never see it because it's uniformly distributed on this huge circle, and most of the time you're looking at a compact interval. So if you take something like the compact open topology, or you take pairings with functions that have some sort of decay at infinity, not in L infinity, because in L infinity there is actually a peak. If you take L infinity over the entire circle, there is actually a peak. But any sort of topology where you ask for convergence on compact sets, you will just see convergence to 0. Okay, so there is a very interesting question, which is to say, if you rescale these fluctuations, what do you get? And you might say, okay, well, this looks trivial. You just look at the second order. You expand, look at the second variation. It's going to be some sort of Gaussian free field, but actually, it's not. It's going to be a white noise, because there is the fact that you restrict the L2 norm to be of order L here actually forces some strong decorrelation. I'm not going to make more comments about this, but this is something that we're also working on. And also something that writers suggested in some other paper. Okay, so I guess when should I finish? Should I finish maybe in 4 minutes? Sorry, so let me just at least state our result. So
yeah, that's fine.
Okay, so writer's result was revisited very recently by Ptolomeo and Weber, who also considered other measures. They considered measures where they say, well, okay, if we put this full power of the nonlinearity, then we know what happens. So let's see what happens when we try to dampen the nonlinearity by putting an L to the gamma. And they find a phase transition in the behavior. If gamma is not too large, then the behavior is similar to Writer's theorem. You can show that basically the field is very, very close in say LP, in some L2 or LP norm to the manifold of solitons. So you have to find some soliton with a random center. But once you've removed that random center, you just see this one function Q rescaled LQL. If gamma is very large, then you can imagine, but it's not trivial, that this guy sort of goes away and you just see an Ornstein-Uhlenbeck process, because they are looking at an expectation with respect to Ornstein-Uhlenbeck. And this is provided that K is large enough. And the reason is that if you take K to be too small, then it may be much smaller than the natural size of the L2 norm, of the Ornstein-Uhlenbeck process. So I guess if you force an Ornstein-Uhlenbeck process to a very small, to have L2 norm that is much smaller than it's supposed to be, then you have this similar sort of phenomenon where it might decorrelate faster. And when gamma is equal to P over 2 minus 1, they show that actually the behavior depends on P. It will be an Ornstein-Uhlenbeck process when beta is small, on some parameter beta. It'll be an Ornstein-Uhlenbeck process when beta is small enough. When beta is large enough, it's some other process. They're able to show it's not Ornstein-Uhlenbeck process, but they don't characterize it. Exactly. All right, so my goal was to just give you some general ideas of what happened, and it took a bit longer than I thought. But let me just get finally to the phi-3,2 model, the model that we consider. We want to consider a similar problem, but in dimension 2. So now the base dimension, which so far was always the dimension of the parameter, right? The dimension of the field was 2, so there was a 2-component field, but we're still looking on a circle. Here we want to look, instead of a circle, we want to look on a torus, T2L. So this is saying minus L squared. Okay, so it's this 2-dimensional torus. And we want to look at this measure here. So what are the features of this measure? It has a base measure, which is the Gaussian free field. Then it has this cubic term here instead of a, for example, a term u to the p. The difference also with what we saw before is we're going to ask that the field be real valued. If you take the field to be complex valued, then you cannot take the cubic power, because then you're looking at some exponentials of like I times the field, and this we don't know how to deal with. So this model was previously considered in physics, of course, and then by Bourgain and Okamoto and Seong. They also looked at it in dimension 3. One motivation for looking at this model is it is known that in the focusing case, so in the case where you try to look at this base measure, but you put here the power 4, then this measure does not exist. Bridges and Slade showed this. It's not possible to renormalize this measure to anything reasonable. In the case of the power u cubed, then you don't have this issue of being sign definite. So focusing or defocusing doesn't really make sense or make a difference. So in terms of integer powers, u cubed is the biggest power that you can consider, unless you consider sign definite powers. Okay, so in dimension d is equal to 2, the Brownian motion is replaced by this free field. So this quadratic term here is replaced by, say, this random variable, where we take e to the 2 pi I x divided by L, and then all renormalized by L, so that the L2 norm over the torus is 1. Then we multiply by Gaussian random variables that are independent, and then we divide by the square root of 1 plus, so there should be a mass term here. We divide by the square root of 1 plus lambda, where lambda runs over all numbers of this form, n over L, the eigenvalues of the Laplacian. So this field here is reasonably nice, but it's very well known that it's not a function. If you take, for example, the expectation of phi squared at a point, then you get infinity, you get a logarithmically divergent series. So that if we want to consider this measure, we need to renormalize it. Okay? So here are the renormalizations of the terms that appear in the measure. You have to basically look at the Fourier truncation of these functions and then pass them through some Hermite, the appropriate Hermite polynomials. And you can show that the limit exists as you remove the Fourier truncation, and it defines some field which is almost a function. It's in the Sobolev space H minus epsilon for every epsilon. So in the end, what we do is we consider this measure. So we have this cubic power, and we have a term here which plays the same role as the mass cutoff. The reason we don't want to put a mass cutoff, and instead we put this guy, is that if you put a mass cutoff, then since we're in the real valued case, all the deterministic or even stochastic dynamics that would have this as an invariant measure, they don't play very well with this mass cutoff. They don't respect the mass cutoff. Whereas if you put just a term like this, then you can construct stochastic or deterministic wave dynamics that actually would be at least formally invariant with respect to this. So the nonlinear Schrödinger equation had this special property that the L2 norm is conserved. So if you added this to the measure, you could still hope that the dynamics would be invariant. This does not work for like hyperbolic dynamics or the dissipative dynamics. So something like a nonlinear heat equation with white noise. Okay, and as I said, 3 is the only power for which the focusing problem makes sense. Okay, so here's our result. We show that in this case, you also have collapse. So it's a bit, it's stated a bit differently. What we say is, if you look at, let's just look at this over here. Imagine you have some function phi, which is continuous of compact support, or maybe smooth of compact support. Continuous is probably okay, but it doesn't matter. So you have some, maybe a bit more than continuous, maybe C1 or C epsilon. So you have this function here that has compact support, and when L is large enough, its support is contained inside of the torus of like size 2L for all L large enough, and we can take the pairing of this field against this function, and we can ask, is this pairing bigger than epsilon? And the answer is, as L goes to infinity, it's very unlikely to be bigger than epsilon. Actually, we can quantify this as well. So it means that in the limit, this field also disappears. You also have collapse for this field. And in that particular case, we have many other difficulties to make the strategy that I explained before. So we don't have this we don't have at our disposal all these Brownian tools. As I said, if you look at Ryder's beautiful paper, everything is written in terms of Brownian motion. Everything is done by hand. It's very useful that you can, for example, use sort of the Markov structure of Brownian motion. Here in this 2D case, we have to do everything more in the spirit of my explanation, just combining functional analysis and variational analysis to show that the field must actually be close to a certain minimizer of a certain variational principle, which in this case actually happens to be equal to 0. Okay, I don't want to take more of your time. Thanks a lot for your attention. Hopefully you learned something.
Thanks a lot, Phil, for a very nice talk. Open the floor for any questions. Maybe I could start off. So in this last, sorry?
Can you hear me?
Yes, I can hear you. Please go ahead.
So, very nice talk. Thank you. My question is, are there results in discrete fields where you have a function instead of Brownian motion?
So are there results where you have what instead of Brownian motion?
In discrete, some discrete function.
Oh, yeah. So there has been a little bit of work on this. One thing that's nice if you take a discrete field instead of Brownian motion, say you take the discrete GFF, is that you don't have these issues of renormalization, and you can try to take various limits, like various small lattice spacing limits and large volume limit at different rates. So I think I don't know if it's a foundational, but a pretty nice result in this direction was this result by Chatterjee from about 2010. It's in CPAM. So he looks at not quite the same. So he also looks at the measure, but it's a microcanonical ensemble, because we saw that since NLS preserves the mass, you could actually, instead of looking, and discrete NLS also preserves the mass, you can actually try to fix the mass or ask that the mass be in some small, some small tube. And that's what he does. And then he shows that if you take the limit of small lattice and infinite volume in some order, so it's not a fully there's some question of in what order you take it and at what rate, then basically what you see is you just see a single soliton. And he interpreted this in terms of some soliton resolution conjecture in PDE, where it's actually expected that if you take a typical solution of NLS, it will decompose into a single soliton or a pair of solitons that move away from each other and some radiation part. And he got a similar result where, like, if you look at the invariant measure for discrete NLS and in a suitable limit, you see a single soliton and some radiation, which is like Gaussian free field fluctuations.
Thank you. Thank you.
Is there another question? So I guess I wanted to ask, is there a defocusing situation in this last model, or?
Yeah, so for phi 3, there's no defocusing. One of the things that's nice or interesting about phi 3 is that it's not sign definite. It can be both positive or negative because it's the third power. It is actually a question. I don't know whether this has been addressed. You could ask, what is the large L limit of the defocusing measures? Because in dimension 2 and in dimension 3, you can look at the defocusing measures. As far as I know, nobody has studied the infinite volume limit of these. There are, let me see. Actually, no. No, actually, that's not true. For dimension 2, you can study the defocusing. I don't know that it has a nice description. So yeah, scratch that. At least in dimension 2, that you can take the limit and you get some defocusing field. And it's characterized, so you don't have a nice characterization like in terms of stationary diffusion, but there is some characterizations in terms of either a variational problem, like a variational problem for the measure, or a something like a Gubinelli, I think, calls this like a forward-backward SDE. So there are some things you can do in dimension 2. In dimension 3, I'm not sure whether the infinite volume limit has been taken. But when you renormalize, the focusing and defocusing doesn't actually have the same meaning anymore, right? Because once you renormalize, it's no longer sign definite. But you can still ask whether the measure makes sense in infinite volume. And in physics, they always work in it, or they almost always work in infinite volume. So probably they believe that there's no issue here.
Let's see. Okay, well, thank you very much. Are there further questions? Phil?
Oh, somebody asked about invariant measure from KdV. Yeah, this has been done in dimension 1. You can look at an invariant measure for KdV. So KdV is a one-dimensional equation. So this has been done, and also it's shown that it's invariant. But KdV is a pretty nice equation because it has this like the main term is this airy, so it has this cubic derivative, so it recovers more derivatives. It has more dispersion, so you can go much lower. Actually, it's shown that white noise is invariant for KdV. And this is much harder, but the Gibbs measure can also be done. Actually, I think there's also some NYU story. I think Cambronero and McKean show that they have like a nice change of variables that sends some Gibbs-type measure to white noise, and this was used by Questel and Valco, I think, as one of the many proofs of invariance of white noise for KdV on the torus. I think that like there's nonlinear transformation that takes KdV to another equation called MKdV, and Cambronero and McKean in another context had shown that if you look at the Jacobian of this transformation, starting from the Gibbs measure for MKdV, it takes you to white noise or something like that for KdV. And so these are all very nice things. And I don't think, even in dimension one, I don't think it's fully explored. I think somebody should write a book about this. It's a lot of very nice computations that come from McKean's papers and some other people. But it's just a slightly different point of view on Brownian motion. I think it's quite nice. Yeah, thanks for your question.
Okay, well, if there are no further questions, let's thank Phil for a very nice and stimulating talk. Thanks, Phil, for coming on.
Yeah,
So,
thank you. See you around. Bye.
Okay, so let's close the seminar. Thank you. Phil, are you still there, or?